The next video talks about dynamic equilibrium and Le Chatelier's principle. We're going to look at a variety of examples of reversible reactions. We're then going to talk about Le Chatelier's principle and then apply it to those reversible reactions, followed by looking at how temperature and pressure as well as concentration in a catalyst can affect the dynamic equilibrium, the position of equilibrium, and hopefully go on to look at some Q&A examples. The Q&A video afterwards, of course, has a more comprehensive library of questions and answers. So in equilibrium, a reaction occurs in the forwards direction. So for instance, nitrogen can react with hydrogen to become ammonia, but when you have an equilibrium, you must have a reversible reaction, i.e. a reaction that can also go backwards. From ammonia, they can then break into hydrogens and nitrogens. When you have a reaction going forward and in reverse at the same time, i.e. a reversible reaction, eventually there must be what's called an equilibrium established. Let's have a look closer at what this means. First, at the start of the reaction, let's say you only had nitrogen and hydrogen. So I've got here the concentration of nitrogen and hydrogen illustrated here around about there, time on the x-axis. As time continues, more of the reactants are going to be used up to make ammonia, so the concentration of your reactants will decrease. Concentration of nitrogen and hydrogen will decrease, fairly straightforward. With time also, as they're decreasing, we are producing more ammonia, so more and more ammonia is being made. The concentration of ammonia in the mixture is going to increase, but initially there was none of it because nothing had reacted. As time continues, eventually the concentration of reactants will not be changing. The concentration of my products ammonia will not be changing because some of these ammonias are going to be made back into the reactants, nitrogen and hydrogen, and some of the reactants are continuing to make ammonia. Eventually that balance reaches an equilibrium, i.e. the concentration of my reactants and products appear stable. This is a dynamic equilibrium in which the forward and reverse reactions are both continuing, as we've just said, but at the same rate, so the concentrations of reactants and products appear to be stable. So you still have reactants becoming products, products becoming reactants, but they're happening at the same rate, so overall the concentrations appear to be stable. The line is horizontal on a concentration time graph. We can now look at a variety of different states of equilibrium. Although in the previous example with the Haber process, I was trying to illustrate a graph that showed the reactants reaching that sort of equilibrium, the products reaching that sort of concentration at equilibrium. Here, at that equilibrium, the reactants have a greater concentration than the products. They could also have been the reactants reaching a lower concentration before reaching equilibrium, the products reaching a higher concentration before equilibrium. Therefore, the products at equilibrium would have had a greater concentration than reactants at equilibrium when the lines are horizontal. Finally, we could also have had an example where the reactants and the products reach a concentration that's identical, not often, but there are some examples when this has happened, is identical. At equilibrium, the products and reactants have the same concentration. We can look at this with respect to the position of equilibrium. So back to this graph, if the reactants have a higher concentration than the products at equilibrium, the position of equilibrium is said to be to the left, towards the reactants. If the products had a higher concentration than the reactants at equilibrium, we can then therefore say the position of equilibrium here would have been shifted towards the right. It's more towards ammonia. The balance is towards ammonia, the products. Or, if the reactants and products had the same concentration at equilibrium, we can say the position of equilibrium is dead in the middle. Hope that was clear. Let's move on. Now looking at Le Chatelier's principle. For a reversible reaction at dynamic equilibrium, such as the example we looked at in the previous page, again I'm using the same Haber process example here for the production of ammonia, when a reaction, that is a reversible reaction, at dynamic equilibrium is in a closed system, which means things cannot be added or removed without intervention. So you could have nitrogen and hydrogen in a barrel, ammonia being produced,
that reversing back to nitrogen and hydrogen in the same barrel, but there's no way for any of those to escape or more to be added unless we choose to do so. So, reversible reaction at dynamic equilibrium in a closed system, the position of equilibrium will shift to oppose any change placed upon it. So, we talked about position of equilibrium. That's going to shift either to the left and make more reactants, or to the right and make more products, depending on what external changes are applied to the system, i.e. the reaction that's occurring.
Let's look at this equilibrium in a different light. Here I've illustrated a container, and in this container I've put nitrogens, hydrogens and ammonia with respect to this sort of proportion here. Within this, gases are bouncing around, nitrogen and hydrogens are colliding in the right orientation with minimum energy greater than the activation energy and becoming ammonias. Ammonias at the same time are breaking down back into hydrogens and nitrogens. That's going on within this container here, to the point where there is now an equilibrium. So the number of nitrogens and hydrogens becoming ammonia are equal to the number of ammonias becoming back to nitrogens and hydrogens. The rate of the forward reaction is equal to the rate of the reverse reaction. That's what I'm trying to say. So let's increase the concentration and see what happens. Here, if I increase the concentration of my reactants, effectively I've disturbed that equilibrium. So here I've put more nitrogens and hydrogens into my container. In order to counteract that change, the position of equilibrium here needs to take away some of the nitrogens and hydrogens I've put in by creating more ammonias. And by creating more ammonias, we're saying the position of equilibrium is shifting to the right. That way, more of these reactants that I've put in and disturbed the equilibrium with are going to become the products. Likewise, if I had reduced the products by taking away some of these ammonias to replace them, some of the nitrogens and hydrogens would have become ammonia as well. The same effect, position of equilibrium would have shifted to the right. Also, it's true, if I had reduced my reactants, let's say I increased my products, as illustrated here, in order to counteract that change, the position of equilibrium would shift to the left, i.e. take up some of these ammonias and remake hydrogens and nitrogens to counteract the change. I've added more products. Counter that change is to make more of those products become reactants. Position of equilibrium would shift to the left. Reducing reactants, same sort of effect. I would have reduced the numbers of nitrogens and hydrogens. Position of equilibrium would have shifted to the left and made more nitrogens and hydrogens to replace the ones I've taken away. So once, having established the equilibrium, disturbing the concentration of reactants or products will cause the position of equilibrium to shift to oppose the change we've placed upon it. Now, let's look at pressure. Here I've tried to illustrate what happens with pressure. In order to increase pressure in my container, I can add more particles, more gaseous particles, colliding more with the container, increasing pressure. Alternatively, I could have even produced a smaller container and have the same particles put into those, smaller volume for those particles, they collide more with the container, pressure goes up. Either way, increasing pressure in order to achieve that higher pressure, more particles in the container, smaller volume for those particles, either way, the system wants to oppose the change in pressure. Now, in order to oppose that change, it can either go to the side that has more gaseous particles or to the side that has less. Well, if there's more gaseous particles, that side produces more pressure. If there's fewer gaseous particles, that side produces less pressure. So, if the pressure is increased, my position of equilibrium wants to oppose that by going to the side with fewer gaseous particles, so more of my reactants would become products. That would reduce the total number of gaseous particles in the container. Likewise, if we looked at the pressure being decreased, the position of equilibrium will oppose that by trying to up the pressure, i.e. it would go to the side that has more gaseous particles, which in this case would have been to the left. More of my products would have become reactants. That would have produced overall more particles, increasing the pressure. So if we decrease the pressure, position of equilibrium would shift to oppose that by trying to increase the pressure, shifting to the left, more gaseous particles. If I increase the pressure,
the position of equilibrium would shift to the side with fewer gaseous particles, i.e. it would have shifted to the right, fewer gaseous particles. I hope that's making clear sense. Let's have a look at temperature. Now with temperature we have an exothermic reaction going ahead, endothermic reaction coming backwards, the forward reaction, backwards reaction both occurring at the same time. It's an equilibrium. If I was to increase the temperature, so my temperature goes up, the position of equilibrium needs to try to take in the extra energy I've put in. To do that, it shifts in the endothermic direction. So increasing the temperature means the position of equilibrium wants to oppose that. It will shift in the side that takes in the extra energy I've put in, the endothermic direction to the left. Endothermic direction, temperature's increased. Opposing this change, the position of equilibrium will shift to the side that takes in more energy, i.e. will cause more of my products to become reactants. So that will overall take in more energy, endothermic direction, backwards. Decreasing the temperature, the system is in equilibrium. It wants to oppose that change, i.e. decreasing the temperature will force the equilibrium to shift to the side that releases energy and ups the temperature, i.e. shifts to the right. That will go in the exothermic direction. Exothermic is the forward reaction, which means more of the reactants would become products. Simply lowering the temperature, disturbing that equilibrium, the position of equilibrium would shift in the exothermic direction. This would oppose the change, shifting the equilibrium to the right, more reactants becoming products, releasing more energy, opposing my decrease in temperature. So let's look, for instance, here I've illustrated concentration. If I increase the concentration of reactants or remove some of the products, reduce the concentration of products. So I add more reactants, reduce more products. To oppose that change that I've imposed, the position of equilibrium will shift. Well, if I've increased reactants, it will shift to reduce those reactants by making more product. If I've reduced products, the same is happening. It will shift towards the products and make more of them. So by increasing reactants or reducing products, I cause the position of equilibrium to shift to the right, opposing the change placed upon it. More reactants, when the equilibrium shifts to the right, it's going to use up those reactants, opposing the change. Less products is going to shift to the right to make more of those products, opposing the change. Likewise, if I was to change the concentration by reducing the reactants or increasing the products, so I've reduced the reactants, the position of equilibrium will shift to the left to make more of them and replace the ones that I've taken away. Or, alternatively, if I increase the concentration of ammonia, my product, again, the position of equilibrium will shift to the left to oppose that change and remove some of those ammonias and make them back into nitrogen and hydrogen, the reactants. So, lower reactants or higher products, I would shift the equilibrium to oppose that change to the left. Hope that's clear. Have a think, reverse the video if you have to go through it more slowly, and let's go on to look at other factors. Before I reveal what happens, have a think. You may already have done Le Chatelier's. Have a think what would happen if I change temperature. After a couple of seconds, I'll show you what happens with temperature. So if the temperature is reduced, to oppose this change, i.e. to bring up the temperature, the position of equilibrium needs to shift. Which way? It will shift in the exothermic direction and generate more energy, releasing that energy. So if the temperature is reduced, to oppose this change, the position of equilibrium will shift in the exothermic direction, which in this case is to the right. The forward reaction is exothermic. That will increase ammonia production. So, when you have an exam question, if the temperature is being reduced, to oppose this change, the position of equilibrium will shift in the exothermic direction should be your line. Then you look at your reaction and decide if it's left or right. In this case, okay, it was to the right, so I said to the right, increasing ammonia production. Likewise, if you increase the temperature, i.e. we're imposing a higher temperature to the system, if the temperature is increased, to oppose this change, the position of equilibrium will shift in the endothermic direction. In this case, to the left, reducing ammonia production, less ammonia being made. Hopefully that was clear. Have a moment to think about it, and then try to think about what would happen if pressure was changed, and I'll reveal what happens when pressure changes in just a moment. So, if the pressure is increased, the position of equilibrium will shift to oppose this change, i.e. it wants to reduce that pressure. So, pressure is increased, the position of equilibrium will oppose this change by shifting to the side with fewer gaseous moles. Fewer, i.e. on the left here I have 1 mole of nitrogen, 3 moles of hydrogen gases, that's 4 moles of gases. On the right there are 2 moles of gases. With respect to the balance of gases, there are fewer moles to the right. Pressure's gone up. By going to the side that has fewer gaseous molecules, the pressure can be brought down. So, if the pressure is increased, the position of equilibrium will oppose this change by shifting to the side with fewer gaseous moles to the right, this process favoring ammonia production. Likewise, if the pressure is decreased, the position of equilibrium will oppose this change by shifting to the side with more gaseous moles. So therefore, by having more gaseous moles, it's going to up the pressure to the left in this process, reducing ammonia production. Higher pressures we impose on the system, on the reaction. The position of equilibrium shifts to oppose that change by going to the side with fewer gaseous moles. In this case, it's to the right, favoring ammonia production. The pressure is decreased. The position of equilibrium wants to increase the pressure. To do that, it's going to oppose the change, the decrease in pressure. It's going to oppose the change by shifting to the side with more gaseous moles to the left, reducing the amount of ammonia produced. I hope that was clear. Have a think about your own explanations and see if your words were similar to what I was trying to explain here. My approach is very simply to talk about what we've done. The pressure's gone up, the temperature's gone down, whichever one we're referring to, what the position of equilibrium wants to do. It wants to shift to the side with fewer gaseous moles, more gaseous moles, exothermic direction, endothermic direction, and then look at your example in the exam question. Is it going to the right or to the left? Is it maximizing or reducing whatever you're producing? Hopefully that was straightforward. We'll look further at exam style questions in a moment. Before we do, have a think. What would be, if the examiner asked, what would be the ideal conditions, not specific numbers, the ideal conditions that would maximize ammonia production, in this case it's the product of course, ammonia production in terms of temperature and pressure. Think about what compromises must be made with respect to those conditions, and then think about the effect of a catalyst. I'll give you a couple of seconds, pause the video, before I reveal what I would say about those. So here, when an industrialist makes ammonia in the Haber process, generally it's around 200 atmospheres is used, 400 to 500 degrees Celsius, and an iron catalyst is used. Let's address these conditions separately. First of all, conditions favoring ammonia production. High pressures, simply because, as we said in the earlier example on the previous page, higher pressure favors ammonia production, as this would shift the position of equilibrium towards the side with fewer gaseous moles, therefore to the right. Lower temperature favors ammonia production, as this would shift the position of equilibrium towards the exothermic direction, therefore to the right. So both high pressure and low temperature favors ammonia production. What compromises must be made? Well, the higher the pressure, the more dangerous it is. The higher the pressure, the more energy you need to use to generate and maintain those pressures. So high pressures are dangerous, but also expensive to generate and maintain. Hence, the pressure must be low enough to be safe and economical, yet high enough for the position of equilibrium to favor ammonia. Said in a very specific way, because if that pressure was decreased, make it safer and more economical, a lower pressure favors the side with more gaseous moles to the left. So that's why I've said the pressure should be low enough to be safe and economical, yet high enough for the position of equilibrium still to be facing that direction, towards ammonia production. Low temperatures, well, again, the compromise. Low temperatures reduce the rate of reaction. So It's good enough the position of equilibrium shifted to the right, but we can't make the temperature so low that it takes a long time, say weeks, to get a decent amount of ammonia. So temperatures have to be reduced to favor ammonia production, but reducing the temperatures reduces the rate of reaction, therefore it cannot be too low, and a compromised temperature is chosen, giving an acceptable rate of reaction whilst keeping the position of equilibrium favoring ammonia production. Saying is a low temperature reduces the rate of reaction, so it cannot be too low. So the compromise is to have a high enough temperature that still pushes the equilibrium that way towards ammonia production. High pressure, low temperature favors ammonia. Can't have it too high because it's expensive and dangerous. Can't have the temperature too low because reduce the rate of reaction. So a catalyst. Now, the Haber process uses an ion catalyst. The catalyst increases the rate of forward and reverse reactions equally, i.e. it does not alter the position of the equilibrium, but simply reaches the equilibrium a lot quicker. So the catalyst doesn't change the position of equilibrium, increases the forward and the reverse reaction equally, therefore reaches the position of equilibrium more swiftly. Hopefully that example with the Haber process, very commonly used in books as well as exams, will help you understand the Chatelier's principle and how to apply it. Let's look at some questions on how we can appreciate reversible reactions more in terms of exams.
So now the Q&A video on Le Chatelier's principle and equilibrium. To begin with, let's look at this question. When P2 and Q react to form R and S2, the following results are obtained when changing temperature and pressure. So this graph represents a change in concentration with time. Which of these reactions correctly represents P and Q reacting? Justify your answer. So you've got the options here. Which of these is going to be correct? Justify your answer. After which, is the forward reaction endo or exothermic? Justify your answer. So here's the information you need. I'll give you a few seconds, pause the video here before I reveal my answer, and then go through the learning points. And so the answer of these, option B was the correct answer, simply because look what's happening. As the pressure is increasing, the position of equilibrium would shift to the side with fewer gaseous moles, and here as the pressure is increasing, the concentration of S2, which is what's shown here, is increasing, indicating that the position of equilibrium is shifting towards S2, towards the right. So the right side must have fewer gaseous moles, which in this case, the only equation that had fewer gaseous moles on the right was option B. 3 gaseous moles on the left, 2 on the right. At the top they were balanced. The next option, C, the right side had more. Option D, they were all balanced. You had 4 moles of gas on the left, 4 moles of gas on the right. What's worth noting is if option A was in equilibrium, pressure would not have had an influence on position of equilibrium, simply because there's equal number of moles of gases on the left and right. Increasing or reducing the pressure, the system can't do anything to oppose that change because neither side has a higher or lower amount of gaseous moles of gas. Same goes to D. 4 moles of gas on the left, 4 on the right. Changing pressure would have no influence on position of equilibrium, whereas part C, if the pressure had gone up, position of equilibrium would shift to the side with fewer gaseous moles, i.e. to the left. In order to go to the right, the pressure would have had to go down in option C. However, this particular example, S2 is increasing, so comparing these two, temperature stayed the same, pressure increased. As pressure increases, position of equilibrium will shift to the side with fewer gaseous moles. If S2 is increasing, here S2 is increasing. If S2 is increasing, therefore the concentration of S2 is increasing, i.e. position of equilibrium shifted to the right. S2 must be on the side with fewer gaseous moles. Option B is the right answer. Now, it also asked, is the forward reaction endothermic or exothermic? Justify your answer. Now, if we compare these two curves, the top one and the middle one, pressure stayed the same, temperature decreased, and as the temperature decreased, the forward reaction must have been exothermic because a decrease in temperature would have meant the equilibrium shift in the exothermic direction. And if the exothermic direction is causing more S2, that must mean the forward is the exothermic direction. Forward reaction is exothermic because as the temperature decreases, the equilibrium shifts to the exothermic direction.
and here it is to the right, favouring S2, i.e. more S2, and the temperature was less. Let's try another question. And when P2 and Q react to form R and S2, here's a reaction shown. The following results are obtained. Which line correctly shows the effect of a catalyst? What you notice is it's an S2 against time. Results without a catalyst is shown in that green line. You now have to ascertain which of these lines answers that question. Justify your answer. I'll give you a few seconds. Pause the video when you're ready. The answer is line B, because a catalyst does not affect the position of equilibrium but reaches the equilibrium more quickly. It's increasing the rate of forward and reverse reaction equally. So we managed to get to position of equilibrium. The concentration of S did not change. Position of equilibrium has not changed, so neither has the concentration of S at equilibrium. However, it managed to get to S's equilibrium concentration quicker. Whereas A is showing, although an increased rate of reaction, A is showing that the S concentration had increased, position of equilibrium would have shifted to the right. C is showing you that there's a reduced rate of reaction, the gradient is less, and S's concentration is reduced. Position of equilibrium has shifted to the left. A and C are incorrect, B is correct, increased rate of reaction, the gradient is steeper, and it gets to the same concentration of S at equilibrium than there was without the catalyst. Okay, let's move on to the next question. Again, have a read. The Chatelier principle, define it. Balance the reversible reaction below. Here it is. What conditions favour sulfur trioxide production in terms of pressure and temperature? What compromises are made when selecting the ideal temperature and pressure for sulfur trioxide production? Effects of a catalyst. Vanadium 5 oxide is the catalyst of choice at this stage of the contact process for sulfuric acid manufacture. How does the use of this catalyst affect the position of equilibrium and therefore percentage yield of SO3? Have a think. I'll give you a few seconds. Pause the video before I reveal my answer. My answer. For a reversible reaction at dynamic equilibrium in a closed system, the position of equilibrium will shift to oppose any change placed upon it. Balancing of this equation, hopefully you got the same balancing as I did. 2 SO2s react with oxygen to produce 2 SO3s. The conditions favouring sulfur trioxide production. First of all, in terms of pressure, what we notice here is there are 3 moles of gases on the left, 2 on the right. To make sulfur trioxide, I need to shift the position of equilibrium to the right. In order to do that, I need to shift to the side with fewer gaseous moles. I need a higher pressure. So, high pressure favours sulfur trioxide production, as this would shift the position of equilibrium towards the side with fewer gaseous moles, therefore to the right, favouring sulfur trioxide. Now, in terms of temperature, well, the forward reaction making sulfur trioxide is exothermic. That means I need to cause a change on the conditions to reduce temperature. That will cause the position of equilibrium to shift in the exothermic direction towards sulfur trioxide. So, low temperatures favour sulfur trioxide production, as this would shift the position of equilibrium towards the exothermic direction, therefore to the right, favouring sulfur trioxide. Have a moment, make sure you're clear about that. And now I'll talk about compromises. So the compromises. High pressures are dangerous, but also expensive to generate and maintain, hence the pressure must be low enough to be safe and economical, yet high enough for the position of equilibrium to favour sulfur trioxide production. Straightforward, I hope. High pressures are dangerous and expensive. I must keep the pressure low enough, but at the same time not too low. That will cause the position of equilibrium to go that way. Therefore, it cannot be too low. It's got to be high enough and favour the right side without being too dangerous or uneconomical. Temperatures. Low temperatures reduce the rate of reaction. Therefore, the temperature cannot be too low, and the compromise temperature is chosen, which is high enough, giving an acceptable rate of reaction whilst keeping the position of equilibrium favouring that way sulfur trioxide production. Yes, hopefully that was clear and straightforward. These are the actual conditions used for the industrial production of sulfur trioxide, the contact process. 2 atmospheres, 400 degrees Celsius, 450 degrees Celsius. Finally, the question on vanadium 5 oxide as a catalyst. It does not alter the position of equilibrium as it increases the rate of forward and reverse reactions equally, simply reaches equilibrium quicker. Hopefully you got the same answers. Let's move on to the next question. Again, this is the Le Chatelier's principle question. Have a look at it. There's a reaction here, enthalpy change, questions on stating and explaining the conditions to increase the percentage yield of nitrogen dioxide in terms of pressure and temperature, what compromises are made, state them and explain them, and of course the effect of a catalyst on the position of equilibrium. I'll give you a few seconds, pause the video before I reveal my answer. So the answer. First of all, looking at this equation, we can see the gaseous reactants and products. There's more gases to the right in terms of moles. It's an endothermic process going ahead. Low pressures favour NO2 production, as this would shift the position of equilibrium to the side with more gaseous moles, therefore to the right. Higher temperatures favour NO2 production. We want it to go in the endothermic direction, therefore to make it take energy in, we're going to need to increase the energy around it so it can oppose it. So therefore I said higher temperatures favour NO2 production, as this would shift the position of equilibrium to the endothermic side, therefore to the right, because it's trying to oppose that change. We impose higher temperatures, it takes the energy in to counteract that change, i.e. endothermic direction. We impose lower pressures, it counteracts that change by going to the side with more gaseous moles, trying to up the pressure. Finally, the compromises. The pressure cannot be too low, as this would reduce the rate of reaction, so it's kept high enough to allow the rate to be higher and the position of equilibrium to still favour NO2 production, i.e. if the pressure was too low, it's too slow. If the pressure, however, goes too high, it would start to go backwards. Therefore, we need the pressure to just be high enough for the reaction to be at a good rate without shifting the equilibrium away from NO2, i.e. still favour NO2 production. Finally, temperature. Although a higher temperature is favourable, it cannot have the temperature too high, as this would be expensive to generate and maintain, hence is kept low enough to be economical and acceptably safe, allowing the position of equilibrium to still favour NO2 production. Can't have the temperature too low. If we up the temperature, it's going to be expensive and dangerous. Can't have the temperature too low, rate of reaction will decrease and equilibrium would shift away from NO2 production. So temperatures can't be too high, but can't be too low either. So we still need to keep the equilibrium favouring NO2 production. Finally, effect of a catalyst does not affect the position of equilibrium, simply increases the rate of forward and reverse reaction equally, i.e. gets to the position of equilibrium quicker. Some of you may feel very confident with these questions by now, and this last question may simply have been fairly too easy. Others are finding this useful to reapply what they've learned about the Chatelier. Let's try another question. So, the esterification of ethanoic acid and ethanol is a slightly exothermic process shown below. Ethanoic acid, ethanol becoming ethyl ethanoate and water. It's a reversible reaction. The delta H is slightly negative. It's a slightly exothermic process. Sulfuric acid is used as a catalyst in this reaction. Both the ethanoic acid and ethanol are weakly acidic, so these two reactants are weakly acidic. Which line shows the effect of increasing the temperature on the pH of the solution? From this pH against time here, we're seeing the change in pH, and I hope what you appreciate is as the original experiment is showing when it levels off, that must indicate some sort of equilibrium. Therefore, the pH has stopped changing. We're not changing the concentrations of our ethanoic acid and ethanol. Have a moment, think, decide, check your answer with mine in a few seconds. So the answer. Line B is the correct answer. Now let's understand why. If we increase the temperature, the position of equilibrium shifts to the endothermic side, which is towards the reactants, making more ethanoic acid and ethanol, so the solution would be more acidic. Here, if I was to increase the temperature, endothermic side is that way, towards the production of ethanoic acid and ethanol, that would have made the pH decrease, making the solution, the mixture, more acidic. Therefore, if I increase the temperature, I expect the line to decrease. Now I've got two options, B and C. What you now need to also appreciate is as the temperature increases, so does the rate of reaction, which is why line B is chosen, whereas line C shows a decreased gradient, a decreased rate of reaction compared to the original line. I hope you followed that. Line A, of course, is showing an increase in pH, a more alkaline solution, i.e. the equilibrium was shifting to the right, which would not happen if we're increasing the temperature because that's exothermic. To oppose the change of increasing the temperature, position of equilibrium would shift to the endothermic side, to the left, making more of our acidic reactants, causing the pH to decrease. Of the two options B and C, B is correct because it also shows an increase in rate. C did not show an increase in rate because the temperature has increased, as I've explained at the bottom here. Now an exam style question. The following thermal dissociation is an example of a reversible reaction when dinitrogen tetroxide is heated. So there's dinitrogen tetroxide breaking down into nitrogen dioxide. The forward reaction is an endothermic process. An enthalpy profile diagram was required with particular labeling, and to write an equation including state symbols for the standard enthalpy of formation of NO2. Draw a Hess's diagram. Use the enthalpy of formation data below to calculate the value of delta H for the thermal dissociation of dinitrogen tetroxide. Here you have two values for delta H formation of N2O4 and NO2. A sample of N2O4 is said to have a distribution of energies. Here's a Boltzmann distribution curve. Show the effect of increasing temperature to T2, and using this, describe what effect this has on the rate of reaction. Question D. Assuming the value of delta H for the thermal dissociation is this value here, positive value, state the Chatelier principle, and then describe with reasons the effect on the percentage yield of NO2, our product, and the color of the mixture if the temperature is increased, pressure is increased, and a catalyst is added. Give you 3 seconds, have a go, pause the video here, and I'll reveal my answer. So my answer. Firstly, question A, B, and C. Question A, enthalpy profile diagram, energy against progressive reaction. I could have written reactants or products. I could have written the actual reactants N2O4 and the products 2NO2, indicating from the reactants energy has gone in, activation energy has come out. Final enthalpy for my products is higher than the reactants because it's an endothermic process. Delta H labeled here as such, increasing from the reactants to products. Part B, write an equation including state symbols for the standard enthalpy of formation of NO2. Now, to form NO2, I need half of N2 in its gaseous state plus oxygen in its gaseous state to give me NO2. Balanced equation, gaseous symbols correct. Part 2, drawing a Hess's diagram. Using the formation enthalpies as shown, they needed me to calculate the enthalpy for this reaction. Step 1, write down what I'm trying to work out. N2O4 becoming 2NO2s, that's the enthalpy of my reaction. Formation of N2O4 was positive 916 kilojoules per mole. Formation of NO2 plus 33.18 kilojoules per mole. Because I'm making 2 moles, I have to times that value by 2. That was step 2, putting the arrows and their values in. To make those, I needed N2 and 2 O2s. That would make my N2O4, and it would also make 2 NO2, so my Hess cycle is complete. Now, delta HR, down that arrow, minus 9.16, up that arrow, positive 33.18 times 2, gives me 57.2 kilojoules per mole. Hopefully you got the same. Now let's go on to the other answers. Stating the Chatelier's principle, that a closed system in dynamic equilibrium will shift the position of equilibrium to oppose any change placed upon it. E part 1, the position of equilibrium will shift in the endothermic direction to the right, so we're referring to the idea that if the temperature is increased, endothermic direction, in this case, endothermic is to the right towards the products, increasing the yield of NO2, because it's brown colored, the mixture becomes more brown. Increasing the pressure will shift it to the side with fewer gaseous moles, trying to oppose that change, which in this case fewer is to the left, so position of equilibrium will shift to the side with fewer gaseous moles, so to the left, decreasing the percentage yield of NO2 and making the mixture more colorless, less brown, because that's colorless. So I said less brown because you may still have some of the NO2s in there. Less brown would be better than colorless, or more colorless. It's saying the same thing. Part 3, adding a catalyst will not change the position of equilibrium, so it will not change the color. Whatever concentrations of these two you have, it's going to stay there. It simply reaches the equilibrium quicker. Hopefully all of you got those marks well and you've compared your answers. The Q&A video for this section has a lot more questions for you to practice with. Good luck.